So good morning to all of you. I'm Alberto Campagnolo from University of Padua. I mainly work on the fatigue design of welded joints. So today I will briefly introduce this topic. So let's move to the outline of this presentation. First of all, I will present you the fatigue failure phenomenon in welded joints, showing you some examples of toe and also root fatigue failure, some of laboratory specimens, but also in welded joints present in industrial cases. After that, I will briefly introduce to you what are the approaches proposed by international standards and recommendation for the fatigue design of welded joints, mainly steel welded joints, according to mainly four approaches. The first one is that based on the nominal stress approach. The second one is the hotspot stress approach or structural stress approach. The third one is the notch stress approach, and the last one is that based on the linear elastic fracture mechanics and the integration of the Paris law. Finally, I will present a brief discussion of the approaches and maybe, if I will have time, also an example of a fatigue approach developed in Padua, so that it is based on the state-of-the-art research and is not included in not yet included in international standards or recommendation. So let's start with the first argument, which is the fatigue failure phenomenon in welded joints. In this slide, we can observe maybe the two most important characteristics of welded joints. In the left-hand side figure, we can see a typical fatigue strength curve, which report the stress range on the y-axis as a function of the fatigue life in the x-axis. We can start observing the fatigue strength curve for the base plain material. The example is a plain plate without any notch effect. We can see that the fatigue strength curve is the highest one. In previous presentation, you have also observed that when introducing a notch, in this example, a hole on the structure, you obtain a fatigue strength reduction, especially at the high cycle fatigue regime, so that this notched plate has a fatigue curve which is shifted down as compared to the plain material. The same occurs when considering a joint, and as welded joints subjected, for example, to pure axial loading. We will see in the next slide that a notch effect stress concentration is introduced due to weldment, so that a fatigue strength reduction, especially in the high cycle fatigue regime, is introduced, so that welded structure are not a good solution to sustain cyclic loading. However, weldments are very cheap, is a cheap technology, so that it is widely adopted in the industrial application. Another important observation is that when considering the fatigue strength, for example, the fatigue endurance limit at the high cycle fatigue regime, we can observe that considering again the base material, its fatigue strength is linearly correlated to the parameter which represents the static tensile strength properties of the material. So that by increasing the static tensile strength of the material, we increase also the fatigue strength of this component. However, when introducing a notch, and especially in the welded component, we observe that there is not this correlation, this linear correlation between the fatigue strength and the tensile strength properties of the material. Indeed, we can observe from this curve that increasing the tensile strength of the base material, we do not increase the fatigue strength of the welded structure. This is due to both the presence of the notch effect, but also the presence of high tensile residual stresses, as we will comment it on the next slide. So these are the most important parameters to be considered when dealing with the fatigue strength of welded joints. The fatigue strength of welded joints is reduced as compared to the base material, and it's not a good idea to adopt high strength materials to generate as welded structure, since the statical properties does not affect the fatigue properties of the structure. The reasons for this observation are due to two main parameters. When considering, for example, cruciform joints, as reported in this figure, subjected to pure axial loading, we can apply far from the weldments a load which is reported in blue color in this graph. If we apply small, reduced, or moderate stress load far away from the weldments, we can observe that locally, that is close to the weld side, we obtain a scaled up stress range. I mean, if the stress range applied nominally far from the weldments is small or reduced, the stress range is the difference between the maximum stress and the minimum stress, as already presented in previous presentation. When we observe close to the weld side locally, we see that the stress range is scaled up. This is due to the fact that the weldment introduces a notch effect. Indeed, the stress flow is perturbated by this geometrical variation to the structure, and the stress flow therefore is perturbated and flow through the this attachment, and not only on the base plate. Another important characteristic is that the welding technology is based on the melting of the materials and on later cooling and solidification of the material. Therefore, when materials are cooling down and solidificating, they reduce their volumes, and therefore they introduce in the structure residual stress state, which is typically very high and close to the heat stress of the base material. Therefore, this residual stress state acts as a mean stress already present on the structure before loading heat, and therefore, even if the nominal applied stress history as a mean stress equal to 0, when going local close to the weld side, this nominal stress history is also shifted up to high tensile mean stresses due to residual stress state. Therefore, the critical location of the welded structure is exactly close to the weldment due to both a notch effect, which shifted up the stress range, and also the presence of a high tensile residual stress state shifted the stress state to high tensile residual stresses. So, as we can imagine, the crack due to cyclic fatigue loading would initiate close to the weld side. Let's go to see some experimental examples of fatigue failure of welded joints. In this first example, we can see a partial penetration butt joint, which has at least 3 possible crack initiation locations. The first one is better represented by the welded side, which is a pre-cracking in the structure. The second one is the weld side, and the third one is the interface between the weldment and the base plate. Indeed, when the weldment is not performed, is not done in a good manner, also the interface between the weldment, which is the melted material, and the base plate could be a crack initiation point. Indeed, when testing this joint under pure axial loading, we can obtain the fatigue failure reporting in the right-hand side figures. We can see that at the weld root side, a crack initiated and propagates through the weld throat. Moreover, also a crack initiate and propagate at the interface of the joint. Indeed, this joint here was done in not a good manner, so the interface is a critical location. But also crack initiate and propagate from the welded side and propagate through the thickness of the joint. As reported in this figure, we can see the cracks initiating from the welded side and propagating through the thickness. Another example could be that of a cruciform joint subjected to pure bending loading, 4-point binding loading. And in this case, the unique critical location is due to the presence of the welded side. When testing under pure bending loading, the crack initiated from the tensile stress region, which is the lower surface of this plate, close to the welded side. We can see from this figure that several cracks initiated from the welded side. After that, they propagated with a typical semi-elliptical surface crack shape through the thickness of the plate. And after that, the static failure occurs in both cases. Another example of experimental failure due to cyclic loading while the joints is that reported in this figure, which is a longitudinal attachment with a weldment which presents also weld ends, start and ends of the weldment. We can see also in this case that when applying a pure axial loading, the critical location are typically the weld ends of the weldment. We can see from this figure and in the zoom that 4 possible crack initiation locations are present close to the weld ends at the toe side. Indeed, we can see that at least 4 cracks initiated from all possible crack initiation location, again with a shape which is the typical one, which is the semi-elliptical crack shape. However, these fatigue cracking behavior for welded joints are not present only on small-scale laboratory specimens, but we can observe similar behavior also on large-scale welded structures dealing with industrial applications. The example reported in the left-hand side figure is a lightweight electric moped frame tested by my colleagues Petrone and Meneghetti in our laboratory. We fixed the rear wheels, and after that we applied, my colleagues applied this load Fx applied to this location by using an hydraulic actuators. This load generates on the frame a bending loading, and we can see on the right-hand side figures that cracks initiated from the tensile stress region of this frame, so that the cracks initiated from the lower surface of the tube. In this figure, we can see that the cracks initiated from the toe side. After that, it propagates inside the tube of the frame. In this figure, instead, we can see that the cracks initiated again at the welded side. After that, it propagates along the weld toe profile. On this other figure, instead, we can see that no crack initiated at the welded side. However, the crack seems to initiate in the middle of the weldment. This is the typical cracking behavior when the crack originates from the weld root side, which is hidden in this figure, so that we cannot see the location of the crack initiation. We can see only when the crack emerges on the weldment surface. Other examples of application, of industrial application, are that of full penetration joints present in the structure of a roundabout carousel manufactured by Zamperla, an Italian company. We have analyzed welded detail which is present in this structure, and is a weldment between a tube and a flange. So the welding, the weldment analyzed is better reported in this figure. Another example is fillet welded joints present in quarter tune Scotch yoke weld actuators manufactured by Flowserve. which is a weldment, fillet weldment present generated between a plate with an hole, which is called the yoke wing, and the tube, so that two plates with holes are welded on the tube with a fillet welded joints, which means that when full penetration joints are generated, only the weld side is present, there is no weld root, while when using fillet welded joints, it means that the joint presents both weld side and weld root side as a possible critical location. We have tested these kind of joints in our laboratory by using a pure axial testing machine. Let me pause the video to avoid sounds. We tested these joints in our laboratory, I said, by using a pure tensile, pure axial loading, so that by applying the loading, we can see in this example, by considering the Zampella joint, by applying the loading to this plate and taking advantage of the eccentricity of the load with respect to the axis of the tube, we can generate on the weld structure both a bending moment and also a torsion moment due to the arm of the load with respect to the axis of the tube. So that this is a case of industrial application and also multi-axial loading condition applied to the weldment. Similar procedure, similar loads is applied also to the control serve joints. After the fatigue testing, we have observed his cracking behavior, which is similar to that of a simple small-scale laboratory specimen. Therefore, for dealing with Zampella joints, we have observed that the cracks originated from the weld side, propagating along the weld profile. In this case, we have observed that the crack, surface cracks, originated due to cyclic loading, can reach surface length on the order of 17 millimeters, so it is a very long crack, and this is typical of large-scale welded structure. Dealing with the depth of the crack, we sectioning this specimen, we can measure the depth of the initiated crack, and we have seen that in this case the crack was at a depth of about 6 millimeters, which is close to the total thickness of the tube. However, we cannot say that this is a full thickness crack, since there is already a ligament which can sustain the load. Dealing with the full serve joint, we have observed that the cracks originates from the weld root side. Therefore, from this figure, we can see that the cracks did not initiate from the weld side between the yoke wing and the tube, but emerges almost in the middle of the weldment surface. As discussed previously, this is the typical cracking behavior of a crack originating from the weld root side. If we section again this specimen, we see the transverse section of this structure. We can see it's not very easy from this figure, but this is the weldment, this is the section of the yoke wing, and this is the section of the tube. We can see that from the weld root side, a crack initiated and propagates through the weld throat. In this zoom, maybe it's more easy to see that the crack initiated from this location and propagates through the weld throat, emerging at the weldment surface, and so we can observe this crack path on the surface. So after having shown you some examples of fatigue failures of welded joints, we can speak about how the international standards and recommendation provided by IAW, which is the International Institute of Welding, what this international organization suggests to design welded structure against fatigue. First of all, let me introduce briefly the loading and damage parameter according to the four different approaches previously introduced. When considering cruciform joints like this one, subjected to pure axial loading, we know, we have discussed it previously, that the weldment introduce a notch effect, stress concentration effect close to the welded side. Therefore, if we plot in this figure in a red color the stress field, we can observe that starting from the nominal stress, we have an increase of stress close to the welded side. The first approach is based on the nominal stress, which is calculated or measured experimentally far away from the crack initiation location, which is the welded side. Therefore, the nominal stress approach is based on the stress which acts on the structure on the plate side very far from the crack initiation location. So that the nominal stress approach does not account for the stress concentration effect due to the presence of the weldment, does not account for the geometry of the weldment, and is based also, on the other side on the global geometry of the joint. So that we will see that the nominal stress approach requires different fatigue strength curve for different global geometry of the analyzed welded structure. Since it does not consider the local geometry, which is typically very similar for different welded structures. Other approaches are that based on semi-local or local stress parameters. One of these are the Hotspot approach, which is based on the calculation or the measurement of stresses at a given distance from the welded side. For example, at a distance of 0.4 times the thickness, which is this stress parameter, and 1 times the thickness from the welded side, which is this stress parameter. After having calculated these stresses, the Hotspot approach requires to linearly extrapolated the stress at the toe location, so that we can define the Hotspot stress. Another approach, which is the local one, is that based on the stress calculated directly at the location where the crack initiated, or in the closed in a close distance from the welded side. So that these approaches are based on the local geometry of the weld joint. They account for the geometry of the weldment, and they require therefore lower number of fatigue strength curves. Another approach is completely different from previous ones, since it assumes that pre-crack is present on the structure, and it is based on the calculation of the stress intensity factor, and using the Paris curve, we can derive an estimation of the residual fatigue life of the pre-crack at the structure. After having introduced the different approaches, a few words about the international standards and recommendation. The Eurocode 3 for steel joints, and Eurocode 9 for joints made of aluminum alloys. They suggest only 2 of the previous approaches. The first one is the nominal stress approach, and the second one is the Hotspot stress approach, which is present only in the appendix of these 2 standards. On the other hand, the recommendation of IAW suggests all previous presented approach, therefore the nominal, the Hotspot, the notch rounding or notch stress approach, and also the linear elastic fracture mechanics approach. We can consider the recommendations of IAW as, in a certain sense, a pre-standards. Indeed, after some years, Eurocodes could take approaches recommended by International Institute of Welding and can include directly in the Eurocodes. So maybe in the future we will see also the notch rounding and the linear elastic fracture mechanics included in Eurocode 3 and Eurocode 9. After having introduced the local and damage parameter, we have to speak about the second parameter, since when performing a fatigue strength assessment, we have to compare always loading parameters with the fatigue strength parameters of the material. So that after having introduced the loading parameter, we have to speak about the fatigue strength parameter. Typically, standards and IAW recommendations reports fatigue strength curves in terms of stress range as a function of the fatigue life, and these curves are fitted on a large number of experimental results generated by considering a given geometry, for example, butt-welded joints, tested under precise load ratio, and by considering a wide range of geometrical parameters. For example, the thickness ranging between 8 and 100 millimeters. Typically, the curves are fitted on about 1,000 experimental results. The curves presents important parameters. The first one is the fatigue strength category, the fatigue strength value, which is called welded category or fat class or fatigue strength of the considered detail. Several names are available in the literature and standards, and this is the strength parameter defined at a given fatigue life, which is typically 2 million cycles. After that, another parameter which is very important to define the fatigue strength curve is the inverse slope, which is typically equal to 3 when dealing with steel welded joints under axial or bending loading. And this inverse slope is valid starting from 10,000 cycles up to about the knee point, which is fixed typically at 10 million cycles. After that, several possibilities are possible. In the case of constant amplitude loading, we can define a different slope, which is typically assumed as M2 equal to 22 to avoid the definition of a constant behavior of a curve, so that the definition of a fatigue limit is avoided for a safety reason. And therefore, we can define a slope, an inverse slope, which is equal to 22 for constant amplitude loading. In the case of variable amplitude loading, instead we can define a different slope, which is typically assumed equal to 5. Therefore, this curve is defined assuming different several hypotheses. The first one is that the probability of survival is fixed at 97.7% for safety reason. After that, we can assume also that high-tensile residual stresses are present in the welded joints, which means that the load ratio is high and typically equal to 0.5. The weld quality is good. The knee point, which is this point, is assumed at 10 million cycles. The misalignments are absent or limited, and the thickness of the joints, the reference one, is typically 25 millimeters, and the environment of the fatigue test laboratory is a non-corrosive one, so that we can define a reference fatigue strength category of our joint, which is this value. However, in a typical application, we cannot assume directly this fatigue strength class, but we have to correct this value by assuming different correction factors. The first one is due to thickness. The second one is due to the quality of the weldment, the environment, the residual stress, and the misalignments. After having corrected the fatigue strength category, we have also to reduce this value by assuming a safety factor due to material. Typically, standards and recommendations propose a list of fatigue strength category, which depends on the global geometry of the joints. So that when dealing with the butt joints, we can use a fatigue category which is FAT 90, which means that the category is typically equal to 90 megapascal, the slope is equal to 3, and so on for different welded geometry. When dealing with semi-local or local approaches, we can say that the category reduces to typically only one or a reduced number of category. For hotspots, the category is 90 megapascal, while for no-stress approach, the typical category is equal to 225 megapascal. Let's go to discuss briefly the correction factors of the fatigue strength category. First of all, the misalignments. We have to take account of a possible offset called E in this figure of the plates, so that when we tested these welded joints under nominally pure axial loading, if there is an offset of the plates, we can induce also a secondary bending loading, which increases locally the stress state close to the crack initiation location, which is the weld toe. So that starting from the fatigue strength curve for no misalignments, therefore E, the offset is equal to 0. When we increase the misalignments of the offset E, we can observe that the fatigue strength reduces. So that we have to reduce the fatigue strength category of our welded joints by taking account of the misalignments. In several standards and recommendation, factor is proposed, K misalignments, as 1 plus 3 the offset E divided by the thickness of the plate. We can see from this figure that the normalized fatigue strength as a function of the normalized misalignment E divided by T, is correlated pretty good by this factor. However, we have to say also that the fatigue strength category and the fatigue strength curve reported in standards and recommendation already included reference misalignments. Since the fatigue strength, the experimental fatigue results used to fit this curve already includes misalignments and offset of the tested plates. Therefore, in this table, we can see that factor K misalignments is already included in the curve. And so we have to include this factor only if it is higher than that reported in this table. Also, spot and no-stress approach already includes some misalignments. Going to the thickness effect, we know also from the first presentation of today that the fatigue strength behavior of the materials are affected by a scale effect. Therefore, when increasing the thickness of the tested component, we have both stress gradient and which is different for large-scale components, and also large-scale components includes typically more defects, and we are also prone to fatigue failure for reduced life as compared to small-scale specimen. We can see also on this figure, comparing the nominal fatigue strength as a function of the thickness, that analyzing joints under bending or axial loading, that increasing the thickness of the plate, there is a reduction of the fatigue strength category, especially for pure bending loading. So that the standards and recommendation typically assume as a reference thickness that equal to 25 millimeters, and after that, for thickness larger than this reference one, they suggest to reduce the fatigue class linearly, or assuming not always linearly, but assuming a relationship between as a function of a ratio between the reference thickness and the actual thickness of the analyzed joint, with an exponent which depends on the considered joints and the condition. Another correction factor is due to environmental effects. We know that using testing joints in environment which is different from the hair, we have typically a reduction of the fatigue strength. This graph, this diagram shows how the same joint, the same tested joints reduces its strength when tested under the seawater environment. It is very difficult to suggest a correction factor, since the reduction of the fatigue strength depends also on the time of exposure, the types of load, the frequency, so that standards suggest only to adopt a reduction factor which is lower than 0.7, and also they suggest to adopt a no fatigue limit, so that also for constant amplitude loading they suggest to adopt a slope equal to 3, also after the knee point equal to 10 millicycles. Another effect which is typically positive for fatigue strength correction is the post-weld treatment. Typically, two different treatments are possible and suggested in the literature and in the standards. Starting from a given welded joints, we can assume we can adopt a treatment to improve the geometry, so that this treatment allows to enlarge the weld toe radius, so that enlarging the radius we can reduce the stress concentration factor, and therefore starting from the this welded condition and from the same applied nominal load, we can reduce the stress range applied locally, and so we can increase the fatigue strength of the joint. Another improvement instead is that which allows to reduce the residual stress state close to the weld toe side. Therefore, by introducing, for example, a negative compressive residual stress state, we can reduce the shifting of the nominal applied stress. And also this treatment allows to increase the fatigue strength of the joint. We can see here from the comparison of several experimental results, the gray curve is that relevant to these welded joints. When we adopt post-weld treatments, we can increase the fatigue strength of the considered joints. For example, by using thick dressing, we can increase the fatigue strength, keeping constant the slope of the curve. By using the ultrasonic impact treatment, we can again increase the fatigue strength and changing also the slope of the curve. The standard recommendation suggests a K factor, correction factor, to increase the fatigue strength to account for this behavior. Typical resulting weld toe profile in this welded condition, we have a very sharp notch close to the weld toe side. By using the burr grinding, we can increase the weld toe radius. By using the thick dressing, we can add material also to increase the weld toe radius. By using the ultrasonic impact treatment, we can introduce compressive residual stresses which tend to close, crack, and to retard initiation propagation, and also to increase the weld toe radius. Another correction parameters is that's related to weld quality. Standards and recommendations typically suggest some features which are not allowed, which are typically cracks due to weldment technology, lack of fusion, inclusion, or root defects, while they suggest also the main requirements in terms of toe radius, acceptable undercut, and cold lab. The table reported here is provided by Volvo Quality Standard, which provide a K factor to account for different geometrical parameters in terms of quality. In this figure, we can observe different quality of a weld toe, a very sharp toe radius, almost equal to 0, which reduces the fatigue strength, and after post-welding treatment, we can enlarge the weld toe radius and so obtain an increase of fatigue strength. Another modification of the fatigue strength is due to residual stress, since in a very large scale structure, we can see that high tensile residual stresses are present, and so that also by changing the load ratio, we cannot observe any modification of the fatigue curve, so that there is no correction due to residual stresses. However, when considering small scale welded joints, we have to account for the fact that this residual stress state is reduced, and therefore, if we analyze the experimental result, we can see that the welded joints, small-scale welded joints, are affected by different nominal load ratio, and therefore the fatigue strength is different, especially when in adopting negative load ratio, which includes compressive stresses. The fatigue strength increases, and therefore when the load ratio is negative, we can have K residual stresses which is higher than 1. So going very briefly to the some details of the approaches, how to calculate stresses. We can start with the nominal stress approach. Standards and recommendation suggest to compare the load parameters with the fatigue strength of the joints. The load parameters is derived from the range, the stress range, which can be calculated directly from classical solid mechanics equation. For example, the load range divided by the section area, in the case of pure axial loading, or the range of the bending moment divided by the section modules in the case of pure bending loading. After that, the load parameters, eventually increased by a safety factor, should be compared with the constant amplitude fatigue limit, which is defined typically for standards and recommendation at 2 million, at 5 million cycles or 10 million cycles, it depends on the geometry, so that we have two cases. If the applied load delta sigma is lower than the fatigue limit, we can assume that infinite life is possible for our welded structure. On the other hand, if the applied load is higher than the fatigue limit or the key point, we can intersect the fatigue curve and derive the expected fatigue life of our welded structure. The important parameters we have already discussed is the category of the joint defined at 2 million cycles and the slope M1. It is important to note that the fatigue strength category is not a function of the material grade, but it depends on the joint geometry and the material class, that is steel or aluminum joints typically. So that standards and recommendation suggest different categories as a function of the welded geometry. This example is taken from Aeroport 3 for steel welded joints. We can see that different categories are suggested, for example, for rolled unwelded products, which is equal to 160 megapascal, while, for example, for cruciform or P joints, as reported in this figure, we have a category between 80 and 40 megapascal as a function of the thickness. For example, again, for K joint, we have also different categories, and in some cases also a modification of the slope. So we have to check carefully the standards and recommendation to take the right parameters. Going future to the hotspot stress approach, this is maybe the most adopted in the industry, since it is typically adopted coupled with finite element calculation, and can be adopted also with strain gauge measurements, so experimental measurements. The hotspot approach is based on this procedure. First of all, we have to model our welded joints. We have also to slice the model to locate, to be sure that finite element nodes are located at a given distance from the weld toe side. Typically, the distance from the weld toe side are equal to 0.4 times the thickness and 1 times the thickness of the considered joint. It is not necessary to model the weldments. It is possible to apply the hotspot stress approach also by avoiding the geometrical modeling of the weldment. After having modeled the geometry, we can define a rather coarse mesh with elements having size on the order of half times the thickness. After having defined the mesh, we can solve the finite element models, and we can calculate the principal stress at the given distance previously defined by slicing the model. So when we can calculate the principal stress at the surface of the welded joints at this distance, and we can extrapolate the hotspot stress. Once having in hand the hotspot stress range, we can enter the fatigue strength curve with a class equal to 90, typical, and we can estimate the fatigue life of our joint. In our figure, we can see that typical local stress distribution is non-linear, and we can separate this stress distribution in three different contributions. The membran stress, which is uniform, the bending stress, which follow the typical trend of Navier, and a non-linear stress, which is due to the stress concentration effect due to the weld toe side. Now, the hotspot stress approach, which is called also structural stress approach, is based on the calculation only of the membran and bending stress, while it neglects the non-linear stress contribution. Since this non-linear stress contribution is generated by the local geometry of the weldment, typically the weld root radius and the attachment angle, which are not always known very well. So that the hotspot stress approach neglects the stress contribution and allows to apply to provide a fatigue strength assessment without knowing exactly the local geometry of the weldment. The application of the approach is possible with different procedures available in the literature. The first one, as discussed in the previous slide, we're taking the surface stress. Another application avoids the geometrical modeling of the weldment. Another possible application is based on the linear interpolation of the stress through the thickness of the joint. Once having the linear stress extrapolated at the surface of the joint, it is important to check that the extrapolation of the hotspot stress catch pretty well the linear trend of the stresses before the weld toe side. So, going future to the notch stress approach, the procedure to apply this approach is based on these three steps. First of all, the local approach considers the actual weld geometry, so it is a local approach, and the advantage is that this approach is applicable to both weld toe and root side using the same modeling approach. First of all, we have to generate the geometry under consideration by introducing at the weld toe side and at the weld root side a reference radius. So we have to modify the actual geometry of the welded structure by introducing a blunt notch with a radius equal to 1 millimeters. After that, we have to define a mesh, and the mesh should be refined close to the critical location of the joint to reach the convergence of the stress parameters close to the toe and root side. After that, we can solve the analysis and calculate the principal stresses at the root and at the toe side of joint. When having the range of the principal stresses calculated directly at the toe side, for example, we can enter the fatigue strength curve and estimate the fatigue life of the structure. A brief introduction of the theoretical background of the notch stress approach. We can consider a notched component. This is the notch with the actual radius equal to R, and this is the typical notch stress distribution I have of the considered notch. Neuber, first of all, observed that the fatigue life of this notched component was not well correlated to the peak stresses calculated exactly at the notch tip, so that this sigma k maximum was not a good parameter to correlate the fatigue life of this component. On the other hand, you observed that another parameter which correlated pretty well with fatigue life of the components was an average stress, average along distance from the notch tip equal to rho star. So that the effective parameter was the average stress along a distance equal to rho star starting from the notch tip. However, the averaging procedure is not easy for typical notch structure, so that Neuber think about proposal also a different procedure to calculate this average stress, and this procedure was to define a fictitiously rounded notch which has a modified notch tip radius as compared to the actual original one. So that Neuber proposed to modify the notch tip radius so that analyzing this new notch component at the notch tip, we can reach a peak stress which is exactly the same as the average stress of the original notched component. So now, if we can derive a relationship between the fictitious radius of the new notched component as a function of the original one, we can define a new geometry of a notched component and very rapidly and quickly calculate the peak stress, which is the effective stress. So that the procedure is very rapid and applicable also to complex notched components. Neuber proposed this relationship between the fictitious notch radius and the actual one, corrected by a support factor, which is a function of the load, and typically equal to 2.5 for steel joints under axial loading, and the microstructural support length, which is a material property, equal to 0.4 millimeters. Calculating this radius and assuming the worst case scenario, which is a sharp notch having notch tip radius equal to 0, we can derive a reference radius, a fictitious radius of 1 millimeters. This radius is adopted by standards and a recommendation by IAW. And this is the reason why we adopted a radius equal to 1 millimeters, as suggested by Rodai, Sonsino, and Fricke. The notch stress approach, therefore, allows to use a single fatigue strength curve to correlate the fatigue, experimental fatigue results relevant to different weather details, which is very useful, and we can apply it also to complex weather structure. This approach is useful also for comparative studies, since it allows to account for the local geometry of the weldment. Therefore, it allows to study what is the effect, for example, of the depth penetration I on the stress magnification factor, and therefore to study what is the effect of changing the penetration depth I on the fatigue strength of our welded joint. The last approach is based on the linear elastic fracture mechanics. When considering a crack, we know that the stress field ahead of the crack as the strand far from the crack tip is tending to the nominal stress applied to the component, while tending close to the crack tip, the stress tends to infinite. So we cannot use anymore the stress parameter to assess the fatigue strength of the component. On the other side, we know from Williams and Irwin that the stress field can be written as a function of this parameter K, which is the stress intensity factor. We can calculate K from engineering formula as a function of the crack depth A, the nominal stress sigma, and shaped factor F, or we can calculate K also from finite element calculation. Once known K, we can use the Paris curve, which correlates the crack growth rate, so that the speed with which the crack, the speed of growing of the crack present in the welded structure as a function of the crack driving force, which stresses the crack, which is the stress intensity factor delta K. so that we can calculate K, and after that we can enter, we can use this curve, and in particular the region 2, the Paris curve, to derive the residual fatigue life of our structure. Indeed, the region 2, which is better relevant to stable crack growth, has a simple expression which correlates the crack growth rate as a function as the K with power law. And elaborating this curve and integrating it, we can derive the estimated fatigue life. IAW suggests to adopt the fatigue life calculation using the inelastic fracture mechanics approach. Initial crack depth equal to 0.1 millimeters, but this should take very carefully, since the estimated fatigue life is very affected by the initial crack depth. So that I suggest to, if possible, measure the initial crack depth on your welded structure and not to assume that's suggested by IAW, if possible. The final crack depth should be assumed, but it is not really important, since it has a negligible effect on the estimated fatigue life. Typically, IAW suggests to adopt half of the plate thickness or the total thickness of the joint for calculation of the residual life. IAW suggests also the Paris curve, which is better reported on this figure, which is correlated pretty well with experimental results taken from the literature. To conclude the discussion of the proposed approach, we have seen the nominal stress 1, structural hotspot, local approaches that based on the notch rounding, and the linear elastic fracture mechanics. We have seen that the nominal stress approach is the most easy to apply, since we can calculate it by hand using a simple solid mechanics formula. However, the nominal stress approach accounts only for the global joint geometry, so that it requires a large number of fatigue strength curve, while going down towards local approaches, we have we can take into account the local joint geometry, and therefore we can use a reduced number of fatigue strength curve. In most cases, we can use only one fatigue strength curve, which is useful in industrial application. Moreover, the accuracy also increased using the local approaches. I think I have no time to present research approaches. Sabrina?
No, you have time. You have time. Yeah, no problem.
Speak for 1 hour. I take maybe too much time, but if you say that I have time, I can take 5 minutes, not more, to introduce also another local approach, which we have proposed in Padua. It has been proposed by Professor Meneghetti. This approach is based on the calculation of the peak stresses directly at the toe side, so that it is similar to the notch rounding approach, but it does not require a modification of the geometry of the weld toe side. On the other side, it requires to model the worst case scenario, which is the sharp notch present at the weld toe side. After having modeled the sharp notch at the weld toe side, we can perform a finite element analysis with a very coarse mesh, and after that we can calculate the peak stress directly at the toe side. We know very well that this stress using coarse meshes is not convergent, since the convergent stress would tend to infinite. We have seen in a previous slide that when analyzing a sharp notch or a crack, the stress tends to infinite. So using a coarse mesh, you cannot catch this behavior. However, the power of this approach is that we use a wrong stress value, which is absolutely a wrong stress value, but we can correct it with a given parameter, which is KFE star, and we can take into account the size of the adopted mesh. Since the size of the adopted mesh influence the wrong stress value. So that take into account the size of the mesh and given correction parameters. Using the opening peak stress, we can estimate quite in a good manner the notch stress intensity factor due to mode 1 loading, typically axial or bending loading. The same is valid when using the in-plane shear stress to estimate the mode 2 loading, and also for the mode 3 loading, we can use the out of plane shear stress calculated at the notch tip, which is the toe side of the weldment. So that we have a free expression to estimate the notch stress intensity factor due to mode 1, 2, and 3 loading. So the approach can be applied also to multi-axial loading condition. And we can use an expression to mix the contribution of mode 1, mode 2, and mode 3 loading. The approach is based on the average strain energy density, and we can define an equivalent peak stress based on the average strain energy density, which includes the mode 1 peak stress, the mode 2 peak stress, and the mode 3 peak stress properly mixed together with the correction parameters, which includes all previously defined. The advantages of this approach is that very coarse meshes can be applied. The geometry, modification of the geometry is not required, since we can define the sharp notch geometry directly from the CAD software. Only one nodal stress value is sufficient, and a free mesh algorithm can be applied. We do not need regulation of the mesh adopted in the calculation. We have applied this approach to a large database of welded joints, starting from very simple laboratory specimens, going down to complex welded geometries, up to industrial case studies, as better reported in these figures. We have considered arc welded joints, typically made of steel, but also aluminum alloys are included. Different geometries with thickness in the range between 2 and 100 millimeters. Different loading condition, axial bending, torsion, but also multi-axial loading condition, such in this case, bending and torsion, also in this case, bending and torsion, and in this case, axial and torsion loading, both in phase and out of phase. We have included weld toe and root failures and analyzed about 1,000 experimental results. To conclude, we have proposed in the literature two different fatigue strength curves. The first one is valid for prevailing mode 1 loading, which is axial or bending loading condition, and it has been validated, fitted on about 1,000 experimental results. Moreover, we have also proposed another fatigue strength curve, which is valid for typically torsion or multi-axial loading condition, and we have validated this curve with about 400 experimental results. More details about this approach are available on a recent publication by Meneghetti and me on International Journal of Fatigue on this year. Is an IMPRESS publication. With this, I have concluded. I suggest only some references: Error Code 3, Error Code 9, recommendation of IAW from Bakker and Fricker, an introduction to metal fatigue, which is a very good technical record from Pedersen, from which I take most of figures. I thank Pedersen for this possibility, and also this publication, which I have already mentioned. Thank you for your attention.